Thanks, John. Really appreciate those kind words. Yeah, so I'm pretty excited for this presentation today. Yeah, it's on AI-driven geomechanical parameter estimation from Televiewer data. Yeah, we can hop right into it. So yeah, the agenda for this presentation is going to be intro to Televiewer data and our automated Televiewer data processing platform Structura. Yeah, I'm going to then talk about how we use Televiewer data to estimate rock mass rating. And then we'll provide a couple model validation examples, and then I'll conclude. Yeah, so
Eric, just before you launch in, I think you might be sharing your other screen, potentially.
Okay.
We're seeing your main PowerPoint. Just give it another shot there. We don't want to miss anything.
Yeah, thanks for pointing that out. Let's see, is that working now?
I see a slide that says Intro to Structura.
Yes, okay. Sorry about that.
Thanks so much.
Yeah, so we've had quite a year on the Structura team. We've had a lot of development across all of our models, our base functionalities. We've added quite a bit. And honestly, there's tons of stuff that I could talk about for a lot longer than this time slot. One of which, of course, is our launching of our web portal. You see some screenshots on the screen now. But yeah, I think I won't spend too much time talking about all the developments, but instead just focus in on the talk here today. And I'll start by talking about kind of like our base functionality with this product. We take in this Televiewer data and we pass it through a structure segmentation model. So this Televiewer data is traditionally used to garner information about structures within the borehole. We try and identify all the structures that we are present within the survey. And then we try and do a bunch of math to find out some of these characteristics for each of these structures. So the depth, the dip direction, the apparent dip, the aperture, and the roughness. So a Televiewer survey, of course, is run after you finish drilling. Yeah, it kind of provides an image of the borehole walls. We then pass each of these structures also to a secondary model, which we call a structure classifier, which aims to identify what each of these structure types are. Yeah, so that's kind of the base functionality of what Structura does. Over this course of the summer, we thought we'd try and be a bit ambitious and see how far we could really take Televiewer data. And so one of the things that we wanted to look at was seeing if we could identify or estimate rock mass rating from Televiewer data. So rock mass rating is a type of rock classification system. I'll save you the trouble of having to read through all of that table there. And really can just be broken down into 5 principal components. We have the strength rating, the RQD rating, joint spacing, joint condition, and groundwater. All of this will sum up to a scale between 0 and 100 relating to the quality of the rock mass. So again, Televiewer data is traditionally used to gain information on the structures in situ. So if we start thinking about each of these constituents, we can start thinking about what we could already calculate and what we would need more information on. For these first 2, RQD and strength, we'll obviously need a way to estimate strength from this Televiewer data. For the joint spacing, well, if we're already identifying the structures and we know their depths, then we might be able to calculate this already. For the joint conditioning, we'll have to find a way to kind of relate our information we gather from Televiewer data to traditional logging practices. And nowadays, we have more sophisticated means of considering groundwater. So we don't actually incorporate in this RMR calculation. So we'll go throughout this presentation, I'll kind of be checking off each of these constituents as I explain them. So we already have groundwater covered. We'll just set that to 10 and omit it from here on out. Next, as I mentioned, we have joint spacing. So joint spacing, again, we have the depths, we have the structures identified. We really just need to then consider what we count as a fracture and how many of these discontinuities we're going to assign PERT. And yeah, so we're able to calculate that already using all of the outputs from Structura. So we can kind of already check that one off. Now this, I'm actually quite excited about. One of the surveys that you record when you do a Televiewer survey is an amplitude survey. And so this is kind of analogous to a Lieb or a Schmidt hammer, where instead of rather a physical object that you're measuring the rebound, instead of colliding the wall rock with a physical object like you would with a Lieb or a Schmidt hammer, you're doing so with an ultrasonic pulse. And you're measuring, instead of that elastic energy back, you're measuring the acoustic energy reflected off the borehole wall. So this acoustic energy is correlated to the rock strength. However, there's several confounding factors, like you might have mud on the borehole wall, you might have a rougher borehole wall, and there might be some issues with the types of probes used. So traditionally, it's been difficult to get actual strength estimated from this amplitude data. However, we were able to train a machine learning model to learn the patterns within the data to get a better sense at estimating rock strength from this amplitude survey. And yeah, we found pretty good success, and I won't spend too much more time talking about this. I was just presented yesterday a paper that we had published online about this model. It's free and available, so if you're interested in this, you can look it up. So if we have strength, we can then check off the strength rating as one of the constituents for RMR. And then RQD, really that is a combination of these past two parameters. It's the count and spacing of the fractures, and also trying to decide what segments of intact rock are hard and sound and should count towards RQD. So putting those together, we are then able to get our RQD counts. And lastly, we have joint condition. This one took a lot more work on our end, but really when you look at it in detail to the table that we use for quantifying joint condition, you can really see that it comes down to three main aspects. That's roughness, aperture, and wall strength. Just to save you again from reading that table, I have them all highlighted here. Yeah, so again, we have a means of calculating wall strength using the strength model. We have a means of calculating roughness and aperture already from our segmentation model when we find the structures within the borehole surveys. So we are able to then use this data and compare it to our standard means of logging joints in the field. And we're able to get estimates of joint conditions for every single fracture within a survey. And so with all of those constituents more or less solved for, that means we were then able to accurately estimate RMR. Well, I might be jumping the gun a little bit here by saying accurately, but we'll dive into that. So here we have some aggregated data. So on the left, we have the RMR estimates from field logged data for 3 drill holes. And then on the right, we have those same 3 drill holes and their Televiewer surveys run through Structura, and we output the estimated RMR values for each of them. And you can look at these distributions and you see that they're quite similar, especially down to the mean and median and the standard deviation. So it kind of gave us an indication that we were on the right path. And so we then were able to start moving on to model validation. So we started processing more and more of these surveys and outputting these geomechanical logs. And we were able to start generating some of these plots to help us validate the model. We'll look at a few of these examples, so we'll kind of step through this first one. In the blue graph here, we have the strength grade, and with all these plots, we have the solid bar graph being Structura's outputs compared directly to these dashed lines, which are the field logged parameter values. And this is a kind of a good example that shows pretty good agreement, especially when you go all the way to RMR at the end here. And yeah. But what's more interesting, I feel like, is when these actually tend to disagree. So Here we can see pretty good agreement in strength grade and RQD, but then the joint condition here actually differs quite severely. And we can go on and actually look at some core photos that align with this. You can see here that we have quite a major coal seam within this run, within this interval, and that the core logger didn't break out to be a separate interval. And they still record, a pretty moderate joint condition value. Although if this, you're considering all this to be one interval, I'd probably more likely side with Structura's estimate of, 0 to consider the weak coal material here. Again, one other way that this can kind of really help with validating and reviewing traditionally gathered field logging data, we can see again a huge discrepancy, but this time across RQD, joint condition, and RMR. And if we look, we can see in the core photos that there's actually a series of lost core around this interval. And so maybe the logger, when they were in the field, didn't place the lost core correctly within the run, or they should have broken it out further. It's hard to say the exact cause of this discrepancy, but it's likely attributed to this lost core. One more example here. Again, we see pretty good agreement across the parameters, except for this joint condition here where we see a pretty severe disagreement. Structura sees these weak beds here, and it averages out to a joint condition value of 0 because it sees these likely coal stringers. However, if you look closely at the core photos, you can kind of see this spun core effect. So perhaps during the drilling process, these coal stringers were broken down and washed out. And again, this is something that you really wouldn't be able to see if you were just purely going off of the field collected data, even using the core photos and trying to do extensive QA using that. So yeah, all in all, in conclusion, Structura can estimate these geomechanical parameters rapidly and consistently. And I think that this can be a really excellent tool for reviewing and extending the coverage of traditionally collected field data, especially in areas of core loss. Yeah, if you don't recover core in a certain section, like there's very limited things that you can do to help QA what was logged over that run. And this whole process really leverages widely available acoustic Televiewer data. So, many site investigation programs collect this data. They use it to get information about the structures in situ, but they don't do anything more with it. And we're just trying to get more out of the data here at the Structura team. And yeah, thanks for listening to my presentation. And again, I apologize for the technical difficulties at the start. Feel free to reach out and let me know if you have any questions.
Thanks so much, Eric. No need to apologize at all. That was fantastic. If you do have questions for Eric, please feel free to reach out to him directly, or you can place them in the Q&A. We'll move us to our final presenter.